Today, we're going to jump right in with a question that sounds simple, but trust me, has a really interesting answer. It's all about a card trip, and the answer lies in the fascinating world of vector analysis. Let's break it all down.
So, picture this. You're on a road trip. The first leg, you drive 60 kilometers straight north. Then, you make a turn and drive 100 kilometers straight east. The big question is, after all that driving, how far are you in a straight line from where you started?
Now, if your brain immediately went, easy, 60 plus 100 is 160 kilometers, well, you've just stumbled on the exact reason why we need to understand vectors. It feels right, but it's not. By the end of this, you'll see exactly why, and you'll have the tools to get it right every single time.
So, to really get why our simple addition didn't work for the car problem, we need to talk about a fundamental difference between two types of quantities we use every day: scalars and vectors.
Okay, on one side, you've got scalars. Super simple, right? They're just a number, a magnitude. Think about temperature. It's 25 degrees. Or time. It's 3 hours. That's the whole story. But vectors? Oh, they're the whole package. They have a magnitude and a direction, like a force pushing up or a car moving west. The direction is just as critical as the number itself.
And that, right there, is the light bulb moment for our car problem. The journey wasn't just about covering distance, it was about covering a certain distance in a very specific direction, and then another distance in another direction. That's why simply adding them doesn't give you the right answer. Direction matters a lot.
Okay, so if we can't just add them up, what do we do? How do we handle these directional numbers? Well, the trick is to break them down into parts that are way easier to manage. Let's build our toolkit.
I love this analogy because it just makes everything click. Vectors are basically just a fancy math-approved way of giving someone directions. Instead of trying to describe a diagonal line, you just say, go this far sideways, then go this far up. And these separate directions, these individual parts, have a name. We call them components. In a 2D world like our map, you've got an X component, that's your east-west movement, and a Y component, your north-south movement. Simple as that.
Right, so the components are like the step-by-step directions. But what about the actual straight line distance, as the crow flies? That's what we call the magnitude. And to find it, we use this handy little formula. And if it looks familiar, it should. It's basically just the Pythagorean theorem you learned in school, dressed up for its new job.
Okay, this is all cool in theory, but let's make it real. We could crunch these numbers with a calculator, sure, but it's way more powerful to see it in action. Let's fire up some simple Python code and really put this to work.
Now, vector addition sounds pretty intimidating, doesn't it? But here's the secret. It is ridiculously easy. You literally just add the x parts together to get your new x part, and then you add the y parts together for your new y part. That's the whole trick.
And look at this. This is what's so cool about visualizing it. We tell the computer, hey, draw me a vector that goes 1 unit east. That's 1, 0. Then we say, now add a vector that goes 1 unit north. That's 0, 1. And boom, the result, our final destination, is exactly where you'd expect, at the point 1, 1.
So, we can add vectors, but what else can we do? Well, what happens when you multiply a vector by a plain old number, a scalar?
This is super intuitive. You multiply a vector by, say, 2, it just gets twice as long, but it keeps pointing the exact same way. But multiply it by a negative number, like -2, and something really cool happens. It still gets twice as long, but it completely flips around, a full 180 degrees in the opposite direction.
Okay, the moment of truth. We've built up our toolkit, we understand components, we know how to calculate magnitude. Let's circle all the way back to that first question about the car trip and absolutely nail it.
It's just 3 simple steps. That's it. First, we'll represent our trip with components. That's a 100-kilometer push to the east, our x component, and a 60-kilometer push north, our y component. Second, we just pop those numbers right into our magnitude formula. And finally, step 3, we just do the math.
And there you have it, the real answer. It's not 160 kilometers. It's about 116.6. That's how far you actually are from where you started. See? That's the power of thinking with vectors. It gives you the true picture, not just the one that feels right at first.